When people hear the word beryllium, they usually picture something incredibly rare, outrageously expensive, and completely out of reach. Some exotic metal reserved for spacecraft, nuclear reactors, and cutting-edge technology far beyond everyday life. Still, that image only tells part of the story, and it leaves out a much bigger reality. It's true that beryllium is used in some of the most advanced industrial fields in the modern world. And yes, it's generally considered a fairly expensive material compared to ordinary metals. But is it really as uncommon in everyday use as most people tend to believe? Or is the truth actually very different from that impression? Hello everyone! As it turns out, the answer is no, not at all. Even though the amount of beryllium, or Be, found within Earth's crust is extremely tiny, this element is used far more widely than most people realize, not just in spacecraft, but in many familiar things that exist all around us in everyday life. For example, cars, smartphones, and countless products and structures surrounding us every single day almost always contain at least a small amount of beryllium somewhere inside them. At the same time, though, this element is also known for being extremely dangerous to human health under certain conditions. Welcome to our channel! So how is something like that even possible in the first place? Let's dive in together and uncover the reason behind it. History of discovery. Beryllium is the chemical element that holds the fourth position of Mendeleev's periodic table. The only elements that come before it are hydrogen, helium, and lithium. Beryllium is represented by the symbol Be, and its atomic number is 4. On the periodic table, it belongs to group 2 of the second period, placing it alongside metals such as magnesium and calcium within the same chemical family. Beryllium is classified as an alkaline earth metal, but its actual behavior is strikingly different from the typical image most of us associate with the word metal. It is incredibly lightweight, with a density close to aluminum, yet at the same time it's dramatically harder and far more rigid. But the biggest difference lies in its mechanical properties, because unlike many ordinary metals, beryllium has almost no malleability or ductility at all. Trying to bend a sheet of beryllium is basically pointless, because instead of flexing, it can crack and snap surprisingly easily. These unusual characteristics all come from the unique structure of its atoms. Beryllium atoms have an extremely small radius, and their valence electrons are only weakly shielded, meaning they are pulled very strongly toward the atomic nucleus. Because of this tightly packed structure, the bonds between atoms inside the crystal lattice become exceptionally strong and rigid. It's difficult to call this behavior typical for a metal, because in many ways, beryllium acts more like an extremely hard yet brittle ceramic material. So even though beryllium is technically a metal, it differs dramatically from ordinary metals in one way after another. And those differences are not limited to its mechanical properties alone. They even extend to something as unexpected as the taste of its compounds. Yes, you heard that correctly, and this strange detail confused the earliest researchers as well. This element was originally named glucinium by the French chemist Louis-Nicolas Vauquelin, who discovered its presence in the natural mineral beryl back in 1798. The name came from the fact that aqueous solutions of its compounds had a surprisingly sweet taste, almost like glucose. So how exactly did chemists discover what beryllium tasted like in the first place? Did they seriously taste it themselves? Surprisingly enough, the answer is yes. Chemists of that era actually tested newly obtained substances directly with their own tongues. If those early researchers had known that this was a dangerous act that could seriously threaten their health and lives, one has to wonder what they would have done. There are no records of severe poisoning during the earliest stages of research, but it would be a mistake to assume that meant beryllium was safe, because later experience gradually revealed that beryllium was far more dangerous than anyone had imagined. However, the serious dangers of beryllium did not become fully recognized and properly documented until the 20th century. Back in the distant year of 1828, when Frederick Wohler and Antoine Bussy independently obtained highly impure beryllium powder, they were still very far from truly understanding all the properties of the element they had managed to isolate. The unusual properties of beryllium. Many of beryllium's strange and highly unusual properties were not fully studied, understood, and practically applied until the 20th and 21st centuries. Among all of its remarkable characteristics, the one that fascinated researchers the most were its extraordinary speed of sound transmission and its unusual transparency to X-rays. When scientists examined it more closely, they discovered that sound waves travel through beryllium at an astonishing speed of roughly 39,000 to 42,000 feet per second. For a metal, that kind of speed is almost unbelievable. For comparison, sound travels through aluminum at around 21,000 feet per second, through iron at roughly 19,000 feet per second, and through copper at only about 15,000 feet per second. There is, however, one material that still holds the ultimate record, because inside it, sound vibrations move even faster than they do in beryllium, reaching speeds of around 39,000 to nearly 59,000 feet per second. That material is diamond. Even so, diamond tweeters used in audio systems remain extremely expensive niche products reserved for a tiny market, while beryllium is used far more often throughout the world of high-end audio equipment. A high speed of sound inside a material means the material itself is extremely stiff, which helps prevent the speaker diaphragm from deforming during vibration. Thanks to beryllium, audio systems can reproduce remarkably pure, crystal-like high frequencies with exceptional precision and detail. That's exactly why beryllium has become widely used in premium speakers and professional studio audio equipment. Still, you should be careful about blindly believing advertisements for cheap audio gear that proudly claims to contain beryllium. Simply using beryllium is already extremely expensive, so in most cases it only makes financial sense in very costly high-end products. Another astonishing feature of beryllium involves the way it interacts with X-rays. Unlike many other metals, beryllium barely absorbs X-rays at all and instead allows them to pass through with very little obstruction. In a way, it almost resembles transparent glass, letting visible light pass through, because X-rays move through beryllium with barely any interference. This property is considered one of the most useful and valuable characteristics of the element. And it's precisely this feature that made beryllium essential for applications such as X-ray tubes, radiation detectors, and even space telescopes. The metal of space. Because beryllium combines several critically important properties at the same time, it has become widely used throughout the field of space technology. Those properties include low density, exceptional stiffness, heat resistance, and remarkable dimensional stability even under extreme temperature changes. Thanks to these characteristics, beryllium is considered an ideal material for spacecraft components, especially telescope mirrors, satellite structural elements, and various parts used in rocket systems. One of the most famous examples is the James Webb Space Telescope. In this telescope, beryllium is used not only in all 18 hexagonal segments of the primary mirror, but also in the secondary mirror and several supporting structures. And this is exactly where beryllium's extraordinary lightness became incredibly valuable, because it weighs only about 1/4 as much as steel and roughly 2/3 as much as aluminum. Weight is extremely important for spacecraft, since every extra 2.2 pounds launched into space can add thousands of dollars in additional cost. For example, the mirrors of the James Webb Space Telescope feature a low-density, thin-walled structure, making them dramatically lighter than the glass mirrors of the Hubble Space Telescope for the same surface area. As a result, engineers were able to create an enormous primary mirror measuring 21 feet across. Another critically important advantage is beryllium's outstanding balance between stiffness and weight. Its extreme rigidity allows the telescope mirrors to maintain their shape with nanometer-level precision without bending or sagging. That stability is absolutely essential for preserving the ideal shape of the optical system, which in turn makes it possible to capture incredibly high-quality images. Stability at ultra-low temperatures is another major property that cannot be overlooked. Unlike many other materials, beryllium structures can easily withstand the extreme cold conditions of outer space. In extremely low temperature ranges, beryllium's thermal expansion coefficient becomes incredibly small. For example, even in environments ranging from 30 to 40 Kelvin, or about -406 to -388 degrees Fahrenheit, beryllium structures barely change shape at all, without shrinking, warping, or losing precision. In other words, the mirror shape created on Earth remains virtually identical once the telescope reaches space. This brings us to another fascinating property of beryllium, something known as the predictability of cryogenic deformation. When engineers manufacture beryllium mirrors on Earth, they can accurately predict how the material will change shape in the harsh conditions of space and incorporate those changes directly into the design beforehand. As a result, once the telescope reaches space, the mirrors settle into their ideal final shape. And finally, another extremely important characteristic is beryllium's diamagnetism, because its weak interaction with magnetic fields makes it highly beneficial for sensitive observation instruments and detectors. When all of these extraordinary properties are combined together, beryllium makes it possible for space telescopes to operate reliably for many years. During all that time, the mirrors can maintain their shape with extraordinary precision, while continuing to capture detailed images of incredibly distant celestial objects. That is exactly why the enormous cost of the beryllium itself, along with the specialized gold coating process used for the mirrors, is considered completely worthwhile. Yes, the large surfaces of the mirrors are actually coated with an extremely thin layer of gold. That coating is only about 100 nanometers thick, and coating the telescope's mirror surfaces required just around 48 grams, or about 1.7 ounces of gold in total. The reason is simple. Beryllium itself does not reflect infrared radiation particularly well. Gold, on the other hand, reflects infrared light extremely efficiently, allowing the telescope to observe in the infrared spectrum and capture the so-called cold universe. At this point, a natural question comes up. Why not use beryllium in ordinary household mirrors as well? The answer is simple, because the cost would become absurdly high for an ordinary household mirror. On top of that, beryllium is difficult to mine and refine, and processing or polishing it requires highly advanced technology. And above all else, the biggest reason it never became widespread is its extremely high toxicity. The dangerous side of beryllium. As we already mentioned earlier, beryllium has an extremely troubling characteristic, what you could call its dark side, and that is its toxicity. Beryllium is an exceptionally dangerous substance when it comes to human health. When inhaled in the form of dust or aerosol particles, extremely tiny fragments containing beryllium can travel deep into the lungs and eventually reach the alveoli, where they begin to accumulate. Inside the lungs, beryllium particles are taken up by cells of the immune system and gradually build up within those cells over time. The biggest problem is that the body often fails to recognize these microscopic amounts of beryllium correctly, triggering an immune reaction that begins attacking the body's own tissues instead. As a result, chronic inflammation develops inside the tissue, and clusters of cells known as granulomas begin forming, gradually replacing healthy lung tissue. Over time, scarring begins to spread, leading to what is known as fibrosis, and the tissue slowly becomes harder and less flexible. The lung's ability to ventilate properly declines, shortness of breath develops, and oxygen levels in the bloodstream begin to fall. What makes the situation even more complicated is that this reaction appears differently from person to person. Some people are especially sensitive to beryllium, and even extremely tiny amounts can trigger a severe immune response. Others may accumulate beryllium inside their bodies for many years without any obvious symptoms at all, only for the illness to appear much later, sometimes anywhere from 5 to 20 years afterward. Even so, complete safety probably does not truly exist anywhere in this world, because in the end, everything depends on how a substance is handled. Beryllium is no exception, and by strictly following proper safety procedures, the risks involved in handling it can be reduced dramatically. If you enjoyed this video, don't forget to leave a like and share it with your friends. Thank you so much for watching. And with that, we'll see you again next time. Goodbye.